Good afternoon. So for those of you who don't know me, my name's Kevin Myers. I'm a network architect with IP Architects, and today we're going to talk a little bit about WISP design. So I know there's a lot of WISPs in here. We talk to a lot of WISPs. I work with a lot of WISPs, and one of the things we always talk about is traffic engineering. How do I manage my traffic through my towers and through my WISPs? So we're going to talk about that a little bit today with a new design that we've come up with. Well, so let me tell you a little bit about myself before we jump into this. Just my background. I've spent about 19 years now in networking. I started in the late 90s. I think one of the things that I'm most proud of is that we've designed and built networks on 6 continents. And actually not so much because of the networks, just because you get to see and interact with cultures and see what the networks do. It's really neat to work on all these different countries and all these different cultures and see how the networks that you build affect different people. So it's something that I think is really neat. I'm also a MikroTik certified trainer and hold MikroTik, Cisco, and Microsoft certifications. And one of the other things that I know a lot of you through that I'm really passionate about is community involvement in networking. So spend a lot of time blogging, writing, going on podcasts, different things to kind of talk about networking and talk about some of the issues in networking and some of the things that we're doing. So probably one of the most notable that I was really happy to be a part of is the Packet Pushers. If you ever watch the Packet Pushers, they're a great group. Ethan Banks and Greg Farrow and Drew Conry Murray, all those guys. I actually got a chance to go on one of their shows a couple months ago and talk about white box networking and networking field day. I'm also a group contributor in WISP Talk and RouterOS and a few others on Facebook. So if you're on there, feel free to hit me up there. I was a delegate for Network Field Day 14 in Silicon Valley in January or earlier this year, where we went and toured a bunch of big tech companies and talked about next generation of networking. I'm very active in the MikroTik forum, so you can also look for me there, and also on another podcast called Network Collective. So you can find all those on the web. Well, I guess my little pointer's not working today. So before we get into the presentation, I do want to tell you a little bit about my company and about IP Architects. What we do is essentially revolves around consulting. So we have a background in network engineering in service provider, data center, and cloud data center. So data center falling between enterprise as well as cloud service providers for data centers. And we do global consulting. We do it all around the world. We've got offices in 3 countries now. We've got offices in Montreal, 2 offices in the US, and most recently we've opened an office down in South America, down in Venezuela, to do consulting down there. We do fully managed networks. We do network monitoring. And we also do load testing and development. That's one of the more interesting things that people come to us for. For an example, we had a large Silicon Valley company come to us and tell us they wanted to be able to put 100,000 connections of a specific type through a MikroTik terminating, and we actually figured out a way to do that for them. So we were able to do load testing in our lab and kind of build some really unique solutions for some interesting problems. So let's talk about the goal of this presentation. And this is one of the things to kind of help you, give you an idea of like why we're talking about this and what this is all about. And hopefully when you walk away from this, you're going to have a few things nailed down. One of the first things I'm going to talk about is if you use OSPF or maybe you use static routes or something other than BGP for routing your WISP, some of the limitations that you hit. This is actually one of the most common reasons people come to us for consulting is they've hit a wall in their routing. They're trying to move traffic around, they're trying to do something, and they've hit a complete wall in OSPF. And once you grow to a certain size, you will outgrow OSPF. It's almost a given. So we're going to talk a little bit about the limitations in OSPF and other non-BGP routing protocols so that when we talk about eBGP, you understand why this is important. When would I use this? We're also going to talk about something called an OSPF transit fabric. This is something that we developed out of our office in Mississippi for a client that needed to solve a very specific problem. We ended up publishing it on our blog, which is subarea51.net. And it allows us to use all the bandwidth between 2 towers. It creates a fabric between the 2 towers to leverage all the available bandwidth. So we're going to talk about that a little bit. And then we're also going to talk about at the end the benefits of using eBGP in communities to build a scalable framework for managing your traffic. How do I manage my traffic? Other than just going to each tower and putting in a bunch of manual custom rules. How do I build an architecture that allows me to pick an exact tower path through my network by subnet and manage traffic that way? So we're going to talk about that. So I told you before we get into the solution, we're going to talk about the problems, because I think it's really important when you're doing network design and you're building networks, it's really important to understand what the problems are and what problem you're trying to solve. And something that we do a lot, since we work in architecture a lot, we always say there's some kind of a business driver that we start with that leads to a technical problem that we're trying to solve. So in this case, we're going to talk about the problems that you run into when using what we call an IGP. An IGP is an interior gateway protocol. It is a non-EGP protocol. So examples of this would be OSPF and RIP are the only two that are really implemented in MikroTik. You've also got EIGRP, you've got ISIS, and there's actually a few more out there that are working on development in the IETF. Mostly they're designed with reachability. So we're going to talk about utilizing OSPF for all forwarding of traffic. So as the network grows, this creates suboptimal traffic flows. What do we mean by that? So let's take a look at a very basic example of, here's a WISP that we've built, kind of a ring architecture, and we've got links on the northern path here where there's 750 meg, and then we've got a southern path that uses 500 meg links. So if we let OSPF, because the radios are what we call sub-rate Ethernet, it's the speed of the physical port on the radio is not equal to the speed that you can actually put down the path, then we have to make sure we adjust our OSPF costs. If you leave the OSPF costs by the default out of the box, then it's going to take the slower path, simply because there's fewer routers in that path. It takes the default cost for gigabit Ethernet, which is 10, and it's going to take the shortest path, which happens to be the slowest path. So how would we go about fixing that in OSPF? So now we're going to see if we're going to make it better or worse. So we can modify the cost on the lower path in OSPF and say, okay, I'm going to make the cost, instead of 10, I'm going to make it 15 and 15 and 15. And make it 5, 5, and 5 on the top, so that's a worse path. So it's a lower cost to get on the path, and that's our new best path up the northern faster side. Everything's great, right? Well, now it's worse, because we just added a tower. And so now we added this tower down here, hanging off the tower there at the very front, and it has a default cost of 10. Well, when it goes into that tower, then you just added more load to that northern path, and maybe because that's the path, you have nothing traveling that southern path, and maybe you really needed to use that, but because you were jockeying around with OSPF costs, now everything's loaded on that side there. So how are we going to solve that problem? So now, like, oh, I want to use both paths. So now we're going to go into OSPF, and we're gonna tune that cost to say, okay, I'm going to go 15, 15, and 15, which gets me to 60 on that top path. And then I'm going to go 20, 20, and 20, which gets me to 60. So now, from the tower where we started and the customer's hanging off of, I have equal paths back. So now we can leverage something called ECMP. If you've never worked with ECMP, it's a mechanism in OSPF that allows you to select more than one path and load balance down more than one path for traffic headed back to a destination. So now I can load balance traffic across both paths by setting my OSPF cost to the same. So everything's great, right? Maybe not. Now we've got to add another tower out of there, and now we've got overloaded paths on both sides, but 250 meg that we can't use on the upper side because we've set equal cost down each side. So because you've got 250 meg there, you're going to start dropping traffic because the flows hash equally. The network thinks they're equal bandwidth. So you're going to be seriously dropping traffic on that side, and you may end up getting overloaded on that side as well. So some of the solutions that you may get into if you have OSPF is you may get into static routing, or you may get into policy routing. And then the problem you have with those is not only do they not scale, but oftentimes they break and fail over. There's a lot of times you put static routes in, a lot of times you put policy routing in that it just doesn't fail over very well. And there's a reason for that. Policy routing is designed to solve very specific problems that you have. It's really not designed to replace a routing protocol. So what we're going to look at as we get into the OSPF transit fabric slides and then getting into the eBGP slides is how do we take a routing protocol and solve these problems that is designed to solve these problems. And I think one of the most important things to understand about OSPF is OSPF was never designed to be a policy protocol. It's designed to be a reachability protocol. It's designed to say, I want to map a path and see how many paths that I can get to certain places, and then I'm going to map and understand those paths. But it was really never designed to say, okay, now how do I leverage those paths and how do I use that? That's really what BGP is for, which is why we're going to get into that and talk a little bit about it. So Here's the second problem that we have when we get into OSPF. The first one was dealing with policy and managing where am I going to steer my traffic to. The second problem you get into is the vast majority of WISPs that come to us for consulting and they want to do a routing architecture redesign. We'll talk about having active and backup paths. So we'll say, okay, I've got this one path and I want it to be active and then I want my 500 meg to be backup. So my effective bandwidth between any two towers there is 750 meg in the top scenario. Or alternatively, very commonly done, is I'm going to take one of those links and make it only for downstream. You'd probably use OSPF cost to do this. And then I'm going to do a different OSPF cost in the other direction, and I'm going to make that 500 meg for my upstream traffic. That's a very common split that we see in WISPs. So the problem comes in is, you think of the applications that flow across ISP networks today. It's, it used to be we were dealing mostly with web pages and you had a little bit of video and then you had music. Well, now it's Netflix and it's YouTube and it's Hulu and you're dealing with really high volume, bandwidth applications that you're trying to compete with a wireline carrier, you're trying to compete with a Google Fiber. You need every single bit of bandwidth you can get. So if you've got 500 meg of bandwidth sitting on tap that you want to use, why wouldn't you use it? And that's kind of the problem that a WISP came to us with, and we were like, well, okay, let's figure out a way to use that. So in going further before we get into the OSPF transit fabric, in the upper half, we have an overloaded active link and an unused backup. And then in the bottom, we have a link that's unused for downstream and then overloaded on downstream. So again, you can see where pinning traffic to different paths for very specific purposes gets you into trouble if you need to leverage that bandwidth. So OSPF alone doesn't work. And I say it doesn't work. OSPF will usually get you to a certain size and a certain scale, but what you'll find is as you get into more towers, you may start out with one tower and then you get to 10 towers, maybe you get to 20 towers. And then when you start getting into like maybe 50 and 60 towers or 100 plus towers, you have a topology that starts to happen in your WISP where you'll have rings and you'll have a partial mesh and you'll have all these things that start to form. And OSPF starts to break down pretty badly. The other thing I really didn't put in this presentation that we've seen in production that's a major issue is typically OSPF convergence will get to the point where when you get to about 2,000 or 3,000 routes in your OSPF table in a single OSPF area with MikroTik, at that point, you're typically going to get to the point where convergence is so slow that the protocol is unusable. So, and there's a reason for that. OSPF is forced to learn the routes of every router that's participating in that area. That's why it's a link state protocol. And so when you have to do that, then that really slows down your convergence, whereas BGP doesn't attempt to learn every path. It really only wants to learn about the prefixes and the policies. And so the solution we're going to show you actually blends OSPF and lets OSPF do the things that it's good at, and then we let BGP do the things that it's good at, and it's kind of a hybrid approach. So, and the thing is with OSPF, again, every time you do a workaround on OSPF, something else is going to come up. You're going to get everything set just right, and then you're going to add another tower, and then all the work you've done is going to be undone again because OSPF is used for something it really wasn't designed for. And so I mentioned this before, OSPF is a reachability protocol, but it's not a policy protocol. The function of link state routing is to map the available paths and speeds to prefixes. And so let's look at some potential solutions. Now that we've looked at the problems and the limitations that some of you may have already hit, some of you may not be there yet. You may be a couple, 3 years away from this, but you'll know it when you get to that point because things are going to start really slowing down. You'll really start to see some serious, when you have a path fail and you get big enough. We've seen in production networks, in fact, there's actually one gentleman here that we solved this problem for. He was going into 30-minute convergence times. It took 30 minutes for his network routing table to converge across, I think it was several hundred towers. So when you get to that point, you want to look at using something like a transit fabric, and you may do an eBGP AS. So the first bullet point, an eBGP AS, this is something we use currently. It's a design that works very well. It's something that we've taken from the wireline carrier world, where you form an eBGP autonomous system over OSPF. So you take your transit subnets and your loopbacks, you advertise them in OSPF, and then you peer on your loopbacks to form an eBGP AS. That's kind of outside the scope of what we're going to talk about today. I just wanted to mention it because that is probably the most common way we solve this problem now and the way we do it. And then what we're going to show you is kind of the next gen. This is the next gen design. But if you want to know more about eBGP-AS, I think I did a presentation on that, the 2013 MUM, I believe. So you can go look up. There's a whole deep dive on how you build an eBGP-AS on the presentation in 2013 in St. Louis. So the second bullet point, combining eBGP and the OSPF transit fabric, it allows for total control of the tower path, and you can use all of the bandwidth between any two towers. So think about that for a second. You can tell a single subnet the exact tower path you want it to go down. Doesn't matter if it's preferred, what the routing protocol says. You can tell it exactly where you want it to go. And what's even better is, let's say you have 4 sectors at a tower, and you have 4 different paths, and you want each of those subnets to travel a different path back to your POP and back to your core. You can absolutely do that. And again, it's not all or nothing. So with this design, while it's something that you can leverage across your entire network, you could put it in a section of your network and then start migrating towards it in pieces. So while we're showing it across an entire network, it certainly is not something that you would have to overlay all at once in one big bang. You could bring it into pieces of the network and then keep rolling it out. All right, so let's talk about what an OSPF transit fabric actually is. That's the name we gave to it, simply because transit meaning we're trying to establish connectivity between 2 points, between 2 towers with subnets. And we call it a fabric because in most, if you look in the data center world, most fabrics are defined as a large number of equal cost multipath hops. And that's what we have here. So we went a number of ways to tackle this. I think we went through, I don't know how many Keurig pods we went through, because we spent about 3 days on this at the office in design before we finally came up with something that worked. And what we discovered is OSPF didn't necessarily need to know the speed of the radios, but we did need to find a way to tell the routing protocol how to balance the traffic to the different speeds that we had in the towers. So if we let the VLANs inherit their default cost, which is 10, and map 6 VLANs on the northern path and 2 VLANs on the southern path, as the traffic comes in for ECMP, it balances by source and destination by flow. It's not by packet. So if you have a conversation to Google, and it will take that and map it down one path. And then if you go from your computer to Facebook, it will hash down another path. And it round robins like that back and forth. So what we found is, by establishing a ratio of traffic, by mapping more VLANs on one side and fewer VLANs on the other, it exactly mirrored the traffic capacity of those radios. So it would be able to use every bit of bandwidth in one direction and every bit of bandwidth in the other direction, so that you can kind of just glue all those together into a single set of links. So 6 VLANs on the top. We did this in a 6-to-2 ratio, which is really a 3-to-1 if you break it down. But that was what we did was we divided the bandwidth. We divided the bandwidth on the bottom into the top, and then came with the closest ratio to match that in the VLANs to get our traffic ratio. And so we realized that we needed 6 VLANs on the top and 2 VLANs on the bottom. Now, because that 6-to-2 fraction breaks down to 3-to-1, you could do it with 3 VLANs and 1 VLAN, but what we found is sometimes you want to add more VLANs, because the more you add, the more granular the traffic flow and the balancing gets. So if you add more VLANs, it tends to get a little bit better on balancing the traffic out. And then conversely, on the southern path, we have 2 VLANs to make up the 6-to-2 ratio to bring that traffic and draw that traffic down on the southern path. Okay, so this is actually we pulled this out of production. So this is, when we first put this on, you can see when we talk about equal cost multipath, there's our default route, and as you can see, it has 8 gateways. It knows 8 ways to get to the default route. So it's going to hash equally down all those paths. So that's what generates the traffic balancing. And then actually looking at the live traffic, in this case, we had a number, I think we had like 7 or 8 radios between the towers. And so we did that with we actually had backhaul 6 and 7 in the test here. And we put our 2 VLANs there, and we put our 6 VLANs down there. And then if you look at the aggregate traffic, if you add that all up, you will see 22.8 meg on backhaul 07 and 6.2 meg on backhaul 06. And if you divide 6.2 into 22.8, you get pretty close to 6-to-2 or 3-to-1 in your ratio. So now, I really want an OSPF transit fabric, but how does it scale? And that is a question we got a lot when we first proposed this. Actually, when we first proposed it, everybody said it wouldn't work. And then we put it into production, it worked, and they said, oh, how does it scale? So we had to kind of think about that, because it's a really legitimate question. Because bringing a lot of OSPF routes into there and doing it between towers, if I wanted to take that across 200 towers, well, that's a lot of VLANs, and that's a lot of OSPF routes. And that's where eBGP kind of came into it, and we started bringing eBGP into the design. And so I think WISPs that are under 50 towers could probably use this as is without needing to layer eBGP on top, unless you wanted eBGP for the traffic engineering piece. Now I'm speaking strictly of how large you can get with OSPF without slowing your convergence down. So I think if you're under 50 towers, you could probably put this in without layering eBGP on top of it. If you're over 50 towers or you have really complex traffic management requirements, I would probably go ahead and couple it with eBGP to get the best of both worlds. And in fact, after we leave here at the MUM, we have one of the clients we rolled this into production for. They really want to get into the eBGP design, and so we're actually going to be putting that into production for the first time here in about 2 weeks. And so eBGP provides a way to limit OSPF. We'll get into this in the drawings. It limits OSPF just between the two towers. So instead of all those routes like flooding around your network in OSPF, they actually just stay contained between the two towers because we're using eBGP. And we'll see how that works here in just a second. Okay, so let's talk about eBGP as a traffic engineering mechanism. We did the OSPF transit fabric. Now let's talk about eBGP and see why this is helpful and what this does for us. So one of the major benefits of eBGP is the ability to definitively select the next hop by matching attributes. So one of the beautiful things about BGP is it has about 11 steps that it goes through called the best path algorithm, that if you don't influence it in any way, it has about 11 different options to evaluate to figure out what is the best next hop. But as an administrator, you can override it and tell it to go anywhere based on a whole number of things. So BGP communities are what we're going to talk about today, and we'll get in a little bit into what that is and how it's helpful to you. And so here we have a WISP that is 5 towers arranged in a ring. We have one POP over on tower 1. It's going out to the internet. And on the path, what we're going to call the southern tower path, we've got multiple links between the towers. So we got about a 900 meg shot between 1 and 2, 900 meg shot between 2 and 3, and then we have dual links of 750 and 500 between tower 1, tower 5, 4 and 3. So effectively, to go from tower 1 to tower 3, I only have 900 meg on the northern path, and I have about 1.2 gig on the southern path. So how does eBGP differ from iBGP? So one of the common misconceptions about eBGP is that eBGP is for the internet, which is really not true. eBGP simply means if you're going to establish a peering to an autonomous system that is not the same autonomous system as what you've set, that is an eBGP peering, because it's assumed when BGP was first developed, it was assumed that a different autonomous system meant somebody else owned that and controlled that. And that was how that was done. The use case for this, if you want to go look at the use case for where we drew this design, Microsoft first proposed this in their data centers several years ago. They were having a problem scaling in iBGP because they were doing hundreds of thousands of servers. And so the only way they could find that they could scale the way they needed to and build the policies they needed to, even just within the data center, was to use a different autonomous system in every rack. And so they literally were doing BGP down to the rack, doing a different autonomous system. And so they were kind of the first ones to do this use case. And now it's blown up into a bunch of different things. So we adapted that to this use case. So you can see we've got 5 autonomous systems here. These are all in what's called the private range that's reserved by IANA. And we've got 65,001 at tower 1, 65,002 at tower 2, 65,003 at 3, 65,004 at tower 4, and 65,005 at tower 5. Now, I put RARIS up here, if you look right there. That just means your regional internet registry. So for those of you that are here in North America, it's going to be ARIN. If you're from Europe, it's going to be RIPE. And there's a whole bunch of other LACNIC, and there are a bunch of other regional registries. You would get a publicly registered autonomous system number from them. Those would go in your BGP edge routers. And so what you can do is, because these are private autonomous systems, you can set a policy at your BGP edge router to strip all these private systems out of the AS path, so that as it advertises to your upstream, all you see is a single public AS. So let's look at, and I try to make this as big as possible because I'm really guilty of doing like tech presentations and everything's really tiny and nobody can read it. So I try to make this as big as I possibly could so that you could see it. But here's where it all comes together. Here's where we combine the OSPF transit fabric and eBGP. So the challenge we have is if you're doing a BGP peering, you normally are going to do it on a directly connected subnet. You're going to have a cable or something stretched between two routers, and you're going to have a directly connected subnet between them, and you'll do a peering. And that's not what we have in this case, because we have two radios, and we have our OSPF transit fabric. So here I put 3 VLANs on the northern path, and I put 2 VLANs on the southern path here. And so what I want to do is I need to establish an eBGP peering across those. eBGP has a function that's supported in MikroTik called multi-hop, so that if the router that you're peering to is not directly connected to you, you can use another routing protocol to advertise the peering address. In this case, we're using OSPF. So everything in blue is related to the OSPF transit fabric. So if you see the blue loopbacks, we have our neighbor adjacencies formed on all those VLANs to build our transit fabric and use all that bandwidth. And then we have a loopback called Tower 1 to Tower 5 and Tower 5 to Tower 1. And so the point of that is we advertise those loopbacks into OSPF because BGP can then use those IP addresses to peer to each other so that these towers can form an eBGP peering. It also has the benefit of once that loopback is learned over OSPF, it sets all those next hops for the transit fabric. Now we go into our red address here. These are the loopbacks that we put on the router that are advertised in BGP. And so when you go to the next router downstream, that if we were to jump over to Tower 4, which isn't in this picture, the only addresses we would ever learn, we wouldn't learn any of the stuff in blue, none of those OSPF subnets or those loopbacks would get learned by the next router. You would just learn the 100.99.1.1 and 100.99.1.5. So this is the answer to the scale problem. The eBGP relationship keeps all of that OSPF complexity and all those VLANs and all those subnets solely contained between those two towers. It never gets advertised outside of those two towers. And it works because eBGP automatically rewrites the next hop. So let's talk a little bit about BGP communities. BGP communities are a field in a BGP route advertisement that you can use to take some kind of an action or give you some kind of identification about a route, tagged with that community number. They can also be used for route identification. It's a 32-bit format where the first 16 bits is typically set to the ASN of the network that you're working on, and the last 16 bits are defined by the operator. That's kind of a loose assignment. You really don't have to do it that way. That's just kind of the standard they recommend that you do. So what we did here is we did a couple things. We built 5 what are called informational communities. So we built, we decided that our public AS is going to be 11111, and the first community was going to match Tower 1, and then 11112 is Tower 2, and so on all the way down to Tower 5. And the sole purpose of those is just to identify where the traffic is coming from. So before we get into traffic engineering, think of how helpful it would be if you could go into a routing table, if you've got a couple hundred towers and you've got tons of routes, to be able to go in and look at the route in the routing table and be like, oh, that came from Tower 67, or oh, that came from Tower 89. You can kind of build some intelligence that you can actually later then use for traffic engineering and all kinds of stuff into your network to identify where it's coming from. Then we're going to identify some traffic paths. We're going to say, okay, anything tagged with 1111200 is going to take the northern tower path. Tower 321. Anything that's 111.201 is going to take the southern tower path, Tower 3, Tower 4, Tower 5, and Tower 1. You could do incredibly complex variations on this. If you had a tower that was an aggregation point and it had a bunch of towers hung under it, let's say you had 4 towers hung under one tower, you could say, I want these 2 towers to go up to the aggregation point and go left, and I want the other 2 towers hung under it to go up to the aggregation point and go right. And so you can build an almost infinite number of traffic engineering communities that you as the administrator set. And so again, this is all arbitrary. It's something that you define. So changing the next hop, how do we do this? And this is something that gets a little bit complicated. We'll actually have a hands-on demo of this so that you can get a better idea of this. So don't feel like you have to digest all of this just from the diagram, because we actually have some stuff that we can get deeper into it and show it in real time. So the way this works is, I'll get my little pointer out here. So here's Tower 3. We're going to take sector number 1. We've assigned a /23 to the first sector of Tower 3, which is 10.10.0.0/23. And we're going to advertise it down both paths in BGP. We've got our peerings built, and so we're going to advertise it. As we advertise it, we're going to put 2 tags on here. We're going to put the Tower 3 community tag, and we're also going to put the tag that we want the southern tower path. 201 is this path down here. So that gets advertised to both these towers, and it gets learned back here at Tower 1, so it learns it down both paths. Then Tower 1 has this set here. Let me walk over here so it's a little bit easier. Tower 1 has it set here to say when I receive a route that's tagged with 200, which is the northern tower path, set the BGP weight for that peer to 32467. If you're not familiar with BGP weight, it is the absolute highest priority way to set preference in BGP for traffic. It trumps everything else that you could possibly do. AS path, local preference, any of that stuff. So the minute you set weight to force traffic out a specific direction, then anything that matches that community is automatically going to get sent that way. No questions asked. Same thing down here. So that's if we had tagged it in 200, which we didn't. We tagged it in 201. But in 201, we said if you match 201, then set the weight of that peering to 32467. And these are all preferences. If one path goes down, then obviously the only path that remains is your best path. So it still fails over. But in this case, because we've done that, and we're going to look on the next slide, what that actually does for us. Oh, do my little thing here. So we're going to look at influencing traffic down a single path. So by tagging the subnet from Tower 3 into community 111.201, we're able to force the traffic along the higher capacity path, leveraging our OSPF transit fabric. We can use all 1200 meg between all those towers, and we can force it down this path. So even though we have 2 more routers here, and the routing protocol would naturally see it as a longer, worse path, we can say, hey, the minute I build out a new sector, I can tag exactly which path I want it to go down. So there's 2 great things that happen here. One, not only are you forcing it down a path, once you've built all these communities in, they're in and done. So the minute you build a new tower and a new subnet, the only thing you have to do to make sure the traffic goes the way you want it is write a very small short route filter, tagging it down the path that you want it to go, and then you already have all the traffic engineering intelligence built into the network. So all the hard work is done, you set a tag and it flies the way you want it to fly. Now we're going to go down 2 paths. So, and you can go as many as you want with this. If you happen to have 8 redundant paths back to your core, back to a POP, you could slice traffic 8 ways if you wanted to. So we can take, we've introduced another subnet here. So we've got 10.10.0.23, that was our first subnet. And that's flowing, I've got this in the downstream direction. So most ISPs are heavy on downstream and lighter on upstream. So we've got it going from the internet back towards the subscriber over the southern path like we talked about the first time. But now we said, okay, I'm going to take the second sector, which is 10.10.2.0/23, and I don't want to load this southern path. I want to load that second sector at Tower 3 down this path. So the only thing I have to do now that we've built all that intelligence in is tag it in that community, and then it automatically flows down that path. And so as you scale out, this gives you the opportunity to really kind of manage your traffic in a very fine-grained way that just is absolutely impossible with OSPF. Okay, so we've got to the point where I've got a couple more slides, but I want to pause and see what questions that you guys have. What questions do you have about this design? Yes, sir.
So I see you're setting weight in one direction. What about
You would set it in the, correct. So for your default route for upstream traffic, if you wanted to do traffic engineering in that direction, you would do the exact opposite on the originating router. So in the lab that I have, you would actually set it in the other direction to set weight for the OSP, like for your
weight for the routes? You're not setting med for the other direction. You're not setting the metric.
You don't need a metric because weight is the highest BGP attribute that you can set. The minute weight is set, it trumps all other BGP attributes.
So you're substituting advertising metric by using a community that causes weight to be applied at the other end.
At each tower, yes.
Okay.
Yeah, at each tower. So you're using it at each tower to make a traffic decision point.
Okay.
Did you find that this method was easier than using an MPLS traffic engineering base?
I am glad you asked that question. So the reason this design exists because there are some limitations in the MikroTik implementation of traffic engineering. So if you are using MPLS and you're using VPN v4 and you want to build traffic engineering tunnels, and normally if the next hop of the traffic engineering tunnel matches the next hop of a route within a VRF, within a VPN v4 VRF, it would go into that traffic engineering tunnel. Unfortunately, that configuration is not supported in Router OS. One of the other limitations that you'll find is that the LDP protocol in MikroTik Router OS is not set for equal cost multipath. So one of the challenges you have is if you want to leverage all that traffic between your towers, the minute you put MPLS onto all of that, you've suddenly, because LDP and the MPLS FIB is now making the forwarding decision, you've basically broken the transit fabric and put all of that traffic down one radio path.
Hey, Kevin.
Hey.
So that kind of leads into the next question about VPLS overlays. Obviously, you can't load it with VPLS because of the source and destination IPs.
So the next, is that the question, is you can't do VPLS on
Right,
this?
it's because it's about routed subnets through the network.
So the first piece of this design we tackled was OSPF transit fabric, like I guess it was about 7 months ago. About 3 months ago, we tackled this piece. We actually have a design in the lab that solves the MPLS problem. And the way we're proposing to do it is by, if you are going to sell an MPLS service and if you need an MPLS service, we're going to look at using another VLAN down each path for MPLS with subnets that are only reserved for MPLS, so that as you need to put an MPLS service on top of that, then you have a subnet that's solely for MPLS, so that non-MPLS bulk traffic that needs to take advantage of all that can go that path. Anything that needs to be MPLS will have another set of VLANs that you can put it onto.
You said LDP didn't support ECMP, but does RSVP, the traffic engineering subtab?
No, so in the implementation, it does not either. So in the implementation, so if you're familiar with Cisco, Juniper, Brocade, you absolutely can solve the problem in the way that you're suggesting. This is actually a very specific response to that limitation of not being able to leverage MPLS traffic engineering to solve that specific problem, specifically within Router OS.
In many of our OSPF networks, we're using OSPF to distribute a public subnet we've assigned to a customer, and that, of course, flows throughout the network.
Sure.
How do you deal with that in this scenario? Because your examples are sort of showing a hierarchical breakdown.
How do you deal with advertising a customer subnet as far as?
Right. So I assign a /32 to a customer, and the next 32 may be on a completely different tower.
Okay. So in that case, if you're doing it at a /32 boundary, then you would probably need to look at tagging communities. You'd have to build communities that map your specific profile. So the communities I used were very generic. They were very simple. They were, we're going to go north and we're going to go south. But ultimately, the communities are whatever you want them to be. So if you wanted to use other BGP attributes to map into the communities, weight is not the only way to do it. It was easy enough for us to do in the lab. There are a number of BGP attributes and then combinations of those communities that you could aggregate together at a point to say, I want you to do this. So this is kind of a starting point. It's really not the end all be all. But you would have to deal with that at the /32 level and assign communities to treat them in the way that you want.
Okay, thank you.
All right, any other questions?
Yep.
Yes, sir.
Implement a way, thank you. Would there be a way inside of BGP in order for it to track, let's say, if you had a heavy snowstorm that would affect the QAM rating of a license link, to where instead of it pushing 700 megs and it's being affected, it's only able to push 400 megs, where BGP could recognize that and alternate to a different route? The
answer is sort of yes. So it's a slightly different problem that we're working on solving. So when I was out, I actually mentioned I went to Network Field Day 14 in January out in Silicon Valley. One of the shops that we visited was Juniper Networks. We visited their global headquarters and they showed us kind of their next gen stuff. One of the things they did, and we're looking at adapting this into MikroTik, is what we call dynamic QoS. So they actually had a problem where they had satellite networks that were dealing with rain fade, and the QoS needed to expand and contract to match the modulation of the links. And so they actually came up with a solution that was able to basically scale QoS to match the modulation, so that you could build your QoS policies appropriately. You could expand that then into, you probably would want to get into some kind of a controller. At that point, there's so much complexity there, you would probably want some kind of centralized, maybe an SDN controller or something to kind of manage all that. But the answer is yes, you could probably rewrite the BGP communities on the fly to match the changing RF conditions, by using a combination of querying SNMP or an API on the radio to get to the modulation, dump that into a controller that they can then intelligently, set communities on the fly to steer traffic where it needs to.
Okay, thank you.
I think we have another one.
Couldn't you also just shut off a VLAN in that case? So
You could.
I discovered my QAM was dropped by.
Exactly. The action that you take probably could be a number of things you could do to decide exactly how you want to react to that. In this case, if you use the transit fabric, you could. The only reason I might not do that is because if I If I have an end-to-end QoS architecture and I have links that don't utilize a transit fabric, then that wouldn't be unacceptable. So I might want to just have end-to-end QoS and then shrink and expand those policies, based on some kind of centralized intelligence.
Okay.
All right. Okay. So we actually built this into GNS3 for those of you that are familiar with GNS3, and we have it over at our booth. So all of you that have a number of questions about it, you can actually see this live. We're going to bring it up on the big TV, fire up the VM. I don't have every single bit of it in there. We basically are just showing that we're influencing on one path, so you can see how the community reacts. But you can kind of get an idea of how the transit fabric works, what it looks like, what the routing table looks like, and what the policies look like actually in the config to do this. So come by the booth and we'll fire this thing up and we'll talk about it a little bit.